How do P, I, and D affect system behavior and PID control? Imagine you're trying to keep a car steady on a winding road. You need to make quick adjustments, smooth corrections, and sometimes anticipate the next turn. That's what a PID controller does in a control system. It combines three parts, proportional, integral, and derivative, to keep things running smoothly. Each part plays a different role in shaping how the system responds to changes. First, the proportional part reacts to the current error, which is the difference between what you want and what you have. If the error is big, the proportional response is strong, pushing the system toward the set point quickly. Increasing the proportional gain makes the system respond faster, reducing the time it takes to reach the target. But if the gain is too high, it can cause the system to overshoot and start oscillating, like a car bouncing past a stop sign. Proportional control alone can't fix a steady offset, meaning the system might settle slightly away from the target. Next, the integral part looks at the sum of all past errors over time. It adds up the small mistakes that might have been ignored by the proportional part. This helps eliminate any steady-state error, making sure the system eventually reaches the exact set point. However, if the integral gain is too high, it can cause the system to respond slowly or even overshoot because it keeps pushing to correct accumulated errors. It's especially helpful when external disturbances or inaccuracies in the model cause persistent errors. Finally, the derivative part predicts how the error will change in the future based on its current rate of change. Think of it as a warning system that anticipates trouble ahead. If the error is increasing rapidly, the derivative acts to slow things down, preventing overshoot and reducing oscillations. It adds damping, making the system's response smoother. But because it reacts to the rate of change, it can be sensitive to noise in the measurements, which might cause jittery control signals. Derivative control doesn't directly fix steady-state error but improves how the system reacts during transients. Putting it all together, the proportional, integral, and derivative parts work as a team. The proportional part responds immediately to errors, the integral corrects long-term offsets, and the derivative predicts future errors to smooth the response. Tuning these three gains involves balancing how fast the system reacts, how stable it stays, and how accurately it reaches the target. For example, if you want a quick response with no steady error, you might use a combination of proportional and integral. If the system tends to oscillate, adding derivative control can help dampen those swings. In real-world electrical engineering applications like motor speed control, temperature regulation, or voltage stabilization, PID controllers constantly adjust inputs based on sensor feedback. They help keep systems stable and accurate, even when conditions change. So, understanding how each part affects the system lets engineers design controllers that respond quickly, stay stable, and reach the desired outcome efficiently. Remember, the proportional part makes immediate corrections, the integral removes long-term errors, and the derivative smooths out the response by predicting future changes. Together, they create a balanced control system that keeps everything running just right.